The random effects model is a linear regression model applied to panel data when the error term follows an error component model. So the setup for this lecture is as follows. I have a stationary and balanced panel with one explanatory variable. I just make this assumption to simplify the notation. There are no problems extending the random effects model to cases where we have several explanatory variables. So I have a linear regression model. YIT is beta 1 plus beta 2 xit plus an error term epsilon it. I make the error component assumption. We have three possible error component models, and I will work with just one of them, namely the one-way with individual specific effects. But everything I cover in this lecture will work equally well for the time-specific effect and for a two-way error component model. So I write my error term epsilon it as an individual effect plus an error term mu it. I make the Gauss-Markov assumptions on the mu it. So the explanatory variable is exogenous with respect to the mu it. The mu its are stationary, they are homoscedastic, and we have no autocorrelation. So next, let us focus attention to the individual specific effects, the alpha i's. We will distinguish between two cases for the individual specific effects. The individual specific effects can be either random or fixed. So if it's the case that the explanatory variable is exogenous with respect to the individual specific effect, that means that the expected value of alpha I conditionally on xi is 0. By xi here we mean all observations for the explanatory variable for individual I. That is, we condition on all time periods for this individual. If this is the case, then we call this individual specific effect a random individual specific effect. To consider a concrete example, let's say that YIT is the production of milk in farm I at time t, or it could be the log production of milk, makes no difference. XIT is the number of cows, or perhaps the log of the number of cows. We would expect beta 2 to be positive. The more cows you have, the more milk you would tend to produce. Milk production will not just only depend on the number of cows, so we have an error term. The individual specific effect in this case is a farm specific effect. Great farms will have a large alpha I and produce more milk compared to a farm with a smaller alpha I, even when they have the same number of cows. The individual specific effect is random if the expected value of this farm specific effect, which it is in this case, conditionally on xi is 0. So what this means is simply no matter how many cows the farm has, the expected value of this individual specific effect is 0. In words, this simply means that there is no general tendency for farms with a lot of cows to have a large individual specific effects, or for firms with few cows to have a large individual specific effects. The individual specific effect is completely random and not determined by the number of cows. It's determined by other things, perhaps the proficiency of the people working in this farm and maybe how happy the cows are. If the explanatory variable is not exogenous with respect to the individual specific effect, then we say it's a fixed individual specific effect. The terminology is a little bit strange, but if you just think of fixed as the opposite to random, it makes it simpler to remember. We know a couple of things about the conditional expectations. For example, we know that if xi and alpha I is correlated, then x cannot be exogenous. So if there is a correlation between alpha I and xit for any t, then the exogeneity assumption will fail and the individual specific effect is fixed. Using the farm example, if there is a correlation between alpha I and the number of cows, it makes no difference which direction it goes. Say that alpha I is larger if you have more cows, then clearly the expected value of alpha I given xi cannot be 0. It must depend on xi. On the other hand, if the individual specific effect is completely independent of all of the xit's, well, then we have learned that conditioning on xi makes no difference, so the exogeneity assumption will hold in this case. You may remember that this exogeneity assumption is somewhere in between no correlation and independence. So for the rest of the lecture, let's assume that we have a random individual specific effect. So here's an important question. How would you estimate this model with a random individual specific effect? Well, let's have a look at the model. Remember, the key condition for OLS to be consistent and unbiased is that the explanatory variable is exogenous with respect to the error term. Will this be the case? Well, all we have to do is have a look at the expected value of the error term conditionally on xi. There is no point in conditioning on other individuals because we make the typical example that cross-sectional units are independent. This is equal to the expected value of alpha I plus mu it according to the error component model. The sum, I can divide it up into two parts, alpha I conditional on xi plus expected value of mu it conditional on xi. So here's the important point. If the individual specific effect is random, then this is 0. We always make the assumption that the mu it random variables are well behaved, so the whole thing will be 0 in this case. Important conclusion, with the random individual specific effect, the explanatory variable will be exogenous with respect to the entire error term. And that means that if I estimate this model with OLS, I will get consistent and unbiased estimates. Now, a model such as this one, where we have random individual specific effects, is often called a random effects model. And what we have concluded is that if I estimate the random effects model with OLS, that will give me consistent and unbiased estimates. However, for OLS to be efficient and for the standard errors to be consistent, we need more. We need all of the Gauss-Markov assumptions. I will not get into the details, but you can show that these error terms will not satisfy the Gauss-Markov conditions, even though the mu it's will. There will be a correlation between the error terms of the same individuals between two different time periods. We know the consequences of this. That means that OLS is no longer efficient and the standard errors are inconsistent. So for a random effects model, OLS is not efficient, the standard errors are bad. What we tend to do almost exclusively with random effects model is to completely abandon OLS and use a different estimator. This new estimator that we use for random effects models is called a random effect estimator. So I'm not going to cover the exact details in this lecture. We'll focus on exactly how to estimate the model using the random effects estimator. You can show that the random effects estimator is consistent and asymptotically efficient. The asymptotically here simply means that if n is large enough, then the random effects estimator is efficient. You can also show that you will get the correct standard errors. They will be consistent. You can also estimate the individual specific effects from this random effects estimator. That is, you can estimate these alphas, and that would be some kind of estimate of the efficiency of a particular farm. So even though I have focused on just one explanatory variable with only the individual specific effects, it's quite straightforward to extend this to several explanatory variables. You can do an error component model with time specific effects, and you can also do the two-way error component model. So let's have a look at the random effects estimator. This is just an illustration, so I'm not going to think too carefully about the specification of the model that I use. It would probably make more sense to run a regression on the logs of the variables, and you can easily make that adjustment yourself. So first, here is the pooled OLS. We do milk, C, cows, and let's just add one more variable, say feed. This will be my pooled OLS. We know that if the correct specification of the error term is a random component model, then these estimates here are consistent and unbiased. They are not efficient. More importantly, these standard errors are inconsistent, making the t-statistics, the p-values, and pretty much everything else inconsistent. So instead, let's estimate the same model using the random effects estimator. In eViews, you would just go to quick estimate equation, just like for the OLS. You go to panel options, and here you specify the effects. If you want to have only an individual specific effect, then you change cross-section. If you want only a time specific effect, then you change period. If you want to have them both, that is, if you want to have a two-way error component model, you change them both. Let's do individual specific effect. That is, let's assume that there are factors that affect milk production that are specific to each farm. So I change this. You have the choice of fixed and random. Pick random if the explanatory variables are exogenous with respect to the individual specific effect. So we are basically now assuming that there is no correlation between the number of cows and the individual specific effect, and there is no correlation between feed and the alpha I. The random effects to the right, the pooled OLS to the left. Assuming that my assumptions are correct, that is, assuming that we do have a one-way error component model with individual specific effects, and assuming that those effects are random, then these estimates are efficient. These estimates are consistent. The random effects estimator is preferable to the pooled version. You can also get the estimates of all the individual specific effects. Just go to View, Estimation, Fixed Random Effects, Cross-Section Effects. The estimate, for example, for alpha 1 is 3300. Farm 1 produces 3300 more milk in the units that milk is measured compared to what we would expect for a farm with this many cows and this much feed. So that would be a fairly efficient farm. If I was the manager of farm 19, I would be very worried. A highly negative individual specific effect. So if you want to do the same thing, but you want to assume that you have a random time specific effect, I guess that would be quite hard to argue for that in the case of farms, but I'm not a specialist on milk production. But the assumptions you would be making in this case is that in certain years the milk production is higher for all farms on average, and in other years the milk production is lower on average. But we can certainly make the assumption. And we can also make the assumption of a two-way error component model, just changing the panel option to random for both of them. This will give us new estimates, and I will be able to estimate both individual specific effects and time specific effects. Doing random effects estimation in Gretel is equally simple. You go model, panel, fixed or random effects. So let's do again milk, explain with cows and feed. The selection here for time dummies will allow you to do time specific effects. We don't want that, we want just individual specific effects, and we pick random effect. Click OK, and here is our random effects estimator. Exactly the same result as we got in eViews.